Hello, Janice.
Hi there. You can hear me, correct?
Yes, I can.
Perfect. I'm just sending you the homework right now that I completed. It's due today, correct?
Yep.
Perfect. So each homework has 1 week before the due date, correct?
Approximately, yes.
Okay. I'm guessing it'll change depending on the assignment and everything.
Yeah. Thanks much for considering it responsibly.
No problem. I was just having some troubles with the apartment Wi-Fi and everything like that, and so thankfully it got fixed. I have everything fixed up now. It might have a couple of issues, so if I end up disconnecting, just be aware that that may be a thing that happens. I'll tell you if there's any issues, and
Okay.
it'll be fairly obvious if anything happens.
Okay. Hi, Kristen. Nice seeing you connected. So I believe you are in the lab, and it's not easy to speak out loud there. Hello, you.
Hello.
Nice seeing you.
Nice to see you.
Whom else are we waiting? Let me check. Oh, we are looking for Mahima, if she decides to join. So I'm going to share the screen. So before we go to the materials, let me bring up a sign up list that we were working through last time. So it is now it is important for Janice. So do you have the link to Janice? Do you have a link to this sign up list?
I might. I would have to check through my emails.
I can quickly share it.
Okay, that should work.
Copy done. I did resend it, and it came from one of the odd mails that I'm not typically using.
Okay, that works.
You see? Okay. So in a week and 2 days from now, we will do presentations on some basic skills related to the course, and I will speak a little bit more about them again. But please look through and select about 3 topics you feel comfortable to present. The number 3 comes from about 4 active members of the course and about a dozen interesting subjects. If there would be a dozen people, it would be like 1 subject per person. So, James, were you able to open?
Oh, yeah, I was able to open it. I just found it. Yep, I see everything. It looks like it is a PBTX file, so Yeah.
Can you just modify? It is there are writing permissions for anyone with the link, so you can type in your name and color highlighted.
Okay. I can do that, and then do I send it right back to you?
No, if you do it in Google Slides right now, we all will see how you do it.
Okay, gotcha. Sounds good. Will do.
Excellent, excellent. Thank you.
No problem.
So we are. I'll put it out of the focus, but we'll bring it back when I see you feeling it. And typically, when someone is logging into this document, it shows how many people are connected and actively editing. So do not download, edit it online.
Okay, gotcha.
Okay, good, thanks. Let me bring these slides. So we are in the computational chemistry summer course. Since it is, we are making main focus on the practical aspects. So during first 20 minutes, I hope it is 20, maybe it takes a little longer, I entertain everyone by showing slides from the full course that is offered in spring semester, but we are reducing theoretical part, and it is mostly entertainment. So while I'm showing lectures, feel free to relax or refresh yourself. But when I'm done showing slides, we'll go to practical aspects. So there are a couple of books which could be reasonable, and the course is organized of 4 chapters. During each chapter, we are in addition to theory, we are covering the set of practical skills, and at the end of chapter, we do presentations so that we can share skills with each other and from different point of view, not only from presented by instructor. By now, we do have several subjects signed up, and Janice, I still do not see your you connected to this link.
Oh yeah. I have to sign in still. So.
Do you plan to do it later, or you have technical difficulties?
I'll probably do it a bit later. I'll do it like literally right after lecture. So I'll get that done real quick.
Let's discuss it right now so that.
Okay. Yeah.
So the goal for practical skills for this for the first 25% of the meeting is to log into servers, clusters, create molecular models of molecules and nanostructures that we want to model, and optimize geometry. On this road, we need to be able to do it with different pieces of drawing software, and we need to see some basic skills of connecting to Linux environment in graphical information forwarding, and some basic Linux skills. If you are aware of the details on CCAST account, you can show how one opens account, what is the concept of a job on the cluster, and in the remaining things, there is a clean and optimized geometry in Gauss view. So basically, you can. I expect you to select 1, 2, probably 3 or 4 and 8. It's like total 3. But it would be nice if you log in and try to make the selection yourself. Okay, so there could be another optional wishful homework for next week, but it will be, I will formulate it in more details on Wednesday. It will be an auxiliary concept that helps all of us to optimize geometry. So it will be mostly finding an explanation of the potential energy surface concept, because this is part of a theory that is behind any optimization of geometry, and I will probably write it in more calligraphic way or type and distribute next time. So I'm going to review what we were doing during the previous meetings, just to refresh. And once again, this is not a theoretical course. Please do not worry if you do not follow each step of derivation. Basically, we do need some language and terminology to explain what we are doing currently and later in the practical aspects of the course. So this little lecture presentations that I'm doing are theoretical background of equations that are behind. Main part of the course is build models and compute electronic structure with right software and right hardware, and then compare observables either to other theories, to experiment and practice a little bit of scientific communications. Everything we do is based on the quantum mechanics and Schrödinger equation, which is problem for eigen states and eigenenergies. And if we apply quantum theory to molecules, we need to set up a definition of a molecule as a collection of positive and nuclear and negative charges. Positive charges are nuclei and negative charges are electrons. So here in this cartoon, positive charges we consider as an example molecular hydrogen. So positive charges are protons, negative charges are electrons, and in order to be more mathematically rigorous, we set up the origin and define position of each particle as a radius vector from the origin. Then one recalls that positive charges repel, negative charges repel, and opposite charges attract. So this can be formulated as Coulombic expression for energy of positive and negative for repulsion or attractive between each pair of particles. And we use here uppercase for heavy ions and lowercase for light electrons. Why we are doing this? Because one needs to, if one needs to take into account quantum properties of molecules and electrons there, and also quantum properties of nuclei, one needs to formulate so-called Hamiltonian, the operator of total energy. And there, the total energy is composed of kinetic and potential. And since we have both heavy nuclei and light electrons, you have kinetic energy, which is momentum square over 2 mass for ions, uppercase. Kinetic energy is square over 2m lowercase for electrons. And then 3 types of Coulomb interaction. V sub nn for Coulomb repulsion of ions, V sub ee for Coulomb repulsion of electrons, and V sub ne for this negative sign for attraction between nuclei, which are symbolized by uppercase, and electrons, which are lowercase. All are vectors, and there are multiple of them. There are indices. So the list of the terms in energy is very long, and therefore we introduce this T and V symbols. The amount of so what mathematically this subject of solving Schrödinger equation is nothing but differential equations, and independent variables in this differential equation is Cartesian projections of each particle. So for each electron there are 3 independent variables, for each ion there are 3 independent variables. So even for this simple H2 molecule there will be 3 plus 3 plus 3 plus 3, 12 independent variables. As soon as we go to anything bigger, it will be wave function, depending on many independent variables, which makes problem undoable. Therefore, one needs to apply tricks. And we want to chop problem onto separate the electronic and nuclear. The blue highlight is terms in the molecular Hamiltonian that relate to electronic problem, and one assumes that one can solve it first and then plug in solution into the rest of molecular Schrödinger equation. So if we practice this trick, then the solution of overall molecular Schrödinger equation will be composed. Let me jump further. Will be composed as a product of solutions for electronic part times the terms that depend on the positions of nuclei of nuclear wave functions. In some sense, about here we can stop the course until the rest is done by computer. But this will be correct only if you would have a computer with unlimited power. Right now, the best world computers and even perspective quantum computers are not able to solve this problem. So one needs to separate variables to prove that in some regime this electronic wave function and nuclear wave function can be found and treated independently and carefully described in which situation it is possible. So in order to practice this separation of variables, and notice here it depends explicitly on the lowercase, and uppercase are just parameter, and here for nuclei it depends explicitly on positions of ions on uppercase. So we are taking this psi overall wave function and plug it into molecular Schrödinger equation. What I'm doing now is a little recital of what we did before. So some details are skipped, and I'm trying to be quick because we need to go to practical aspects. So in this molecular Schrödinger equation, there are 4 terms: kinetic nuclear, nuclear repulsion, solution of electronic part, and eigenvalue of energy. So four terms. We can write them this one line per term, and then plug in this summation of products. Plug in this summation of products. So total 4 terms. 1, 2, 3, 4. The solution for Greek phi for electronic part is already assumed to available. The solution for nuclear part, chi, this looks like English Latin X, is not known. So we need to find chi, and we also need to separate to prove that they are independent. This can be done by removing phi sub a. Removing wave function can be done by practicing so-called orthogonality property. So if phi are good functions, then multiplying functions with different indices, or maybe same indices, and integrating them over all positions of electrons, well, you will get either 0 or 1. So in order to practice this orthogonality, we are plugging in this integral over dr phi sub beta, integral over dr phi sub beta from the left part in each term of equation. And if you practice this integration, we hope that we will get either 0 or 1 and get rid of electronic wave functions, thus getting equation only for chi, for Greek chi. Just a second. Okay, good. So, if we follow this protocol for last 3 terms, for terms 2, 3, and 4, we indeed get rid of phi sub a. And we, as a price for it, we replace index A with index B everywhere. But for the top term, we are getting matrix element. We get phi on the left and phi on the right with different indices, and in between there is a symbol T, which is kinetic energy of nucleus. This operation is non-trivial because in quantum theory we cannot swap order of wave functions and operations, or if you make this swap of the order, we pay price for it. And if we practice, if you try to find this, so phi, and this t in between, one needs to remember that t is the second order derivative because momentum is derivative over space. And if we plug in nuclear momentum into here, then it will be this first term will be nothing but practicing chain rule for differentiating the product of nuclear and electronic wave functions. So if one carefully does this procedure, there will be totally 4 terms, but 2 of them coincide, so 4 terms. The cross terms, where there are derivatives over electronic and nuclear over positions of nucleus, a derivative over electronic over positions of nucleus, and those are crazy. So let's just go away from math and think. These terms tell response. Oh, I see question. Eugene, do we also learn molecular dynamics? Oh, yes, we do. And it will be especially in the chapter 3. We will do ab initio molecular dynamics, which is much more rich, reliable, and applicable to bond breaking and bond formation. Thank you for asking it. So continuing back to what I was telling. So this term in 2 terms in green box is response of electronic structure to elongation of bonds, which from chemical intuition, if we expand or contract bonds, something may change in properties of molecule, like color or but it is additional thing that we can neglect if the bonds are not elongated or contracted. While the first term here is very, very standard and normal term. So it's just applying second derivative over position to wave function that to nuclear wave function also depends on positions of nucleus. So it is a regular standard good kinetic energy. So red is good, green is bad. And we stopped last week on this slide, which is summary. So we didn't arrive here yet, but it is our goal. I will try to arrive to this slide very soon. So if everything is done correctly from molecular Schrödinger equation here, we will arrive to separate equations for electronic part and nuclear part that one can process independently. And this nuclear part later will lead to molecular dynamics that you is asking about. So do not worry if material goes too quick. This is primarily for terminology. The derivations and explicit equations will never be in serious portion of a credit. We'll do more practical things. But if later one of us or all of us need to write papers or paragraph in the experimental work about computations, one may need to explain which equations have been solved computationally and list approximations in a reasonable way. So done with review, beginning a little bit of new material. I borrowed ideas from Wilhard May, who was in my thesis committee 20 years ago. And main thing that we already considered, and here I just give a little of notations, is taking second derivative of product of two functions. And there is a important chemical content behind these derivatives. So this one is nuclear, this one is electron. And second derivative over nuclear position is kinetic energy of nucleus. So we carefully practice first, second derivative, taking first derivative of product is first unchanged derivative of second, derivative of first, second unchanged. And we arrive to the thing that if you carefully do it, we'll arrive to think that there will be, again, red and green. Good part, which is called pure kinetic energy of nucleus, and bad part, which is a mixture between electronic and nuclear degrees of freedom. So response of electronic wave functions to elongation of chemical bonds. We do want to forget, to remove, to assume that this term is not available, is not included. We want to artificially remove it as an approximation. And this is very possible and acceptable if we look at low temperature, at equilibrium geometry of molecules. If there are no chemical reactions, if we look only reactants or only products, if we are not including transition states. When this approximation, I'm going one slide back. So the goal is to erase this green box. So when this approximation is not acceptable, when material is hot, really hot, not room temperature, but like 2000 Kelvin, when it goes to plasma, when there are chemical reactions, when molecules break on pieces, when molecules are irradiated by strong laser pulse. So I think it will be a situation of that you is mostly interested, when laser irradiation facilitates chemical reaction. So if we are in this limit, then unfortunately neglection of this terms is not welcome. And also, if there is electron transfer, this terms cannot be neglected. So thank you for staying here. We are going a little bit over time, but I hope, no, I want to be quicker, but it will be a few slides more. Okay, so once again, when we were practicing second derivative of product, we've got three types of terms. Actually four, but one, there were two equivalent terms. So when the derivative, second derivative over uppercase R is applied to nuclear wave function, we call it pure kinetic energy. And when it is a cross derivatives, or when, this one should be erased, or when the derivative is applied to electronic wave functions, so elongation of nuclear of bonds affect electronic properties. This is mixture between electronic and nuclear degrees of freedom. And there were two scientists, Born and Oppenheimer, who suggested that in 99% of practical chemistry, one can neglect these terms. And there, maybe not only for this, but in Los Alamos, the heart of American science, it's a small city in New Mexico, one of the main streets is called after Oppenheimer. So B and O, Born and Oppenheimer. If one takes, so here it was shorthand notation, and there is a full notation that we are not going to reproduce, but just showing you here the derivative, second derivative over nuclear over interatomic bonds of electronic wave function. Second derivative, and here it is cross term. First derivative over chi, first derivative over phi and chi. So those terms are assumed neglected in most practical chemistry, but we need to give name for something that we remove. And when this is when we change something slowly, when there is no drastic transformations, one calls it adiabatic. When there are drastic transformations, one calls it non-adiabatic. So this term is called non-adiabatic. So non-adiabatic term in molecular Hamiltonian. And we are going to neglect this term. Sometimes in literature it's called theta AB. Its leading term in here is the first derivative of electronic wave functions over positions of bond times momentum. So this momentum comes from DDR, definition of nuclear momentum, and we may return to this equation at the very end of the course. By now, our goal is to forget it as soon as possible. So here is our molecular Schrödinger equation. Last three terms, 2, 3, and 4, already got rid of electronic wave function, and term number 1 does have pure kinetic energy of nucleus and non-adiabatic term. Our goal is to remove it and pretend that it never existed. Then we can do wonders, and we can describe big models and find their properties easily, or relatively easily. With this term, it becomes a very challenging problem that we may briefly look at the end of the course. So, if we neglect this term, and if we stop writing it in the column and rewrite it in the row, we can put the nuclear wave function out of brackets, and inside the brackets we will have pure kinetic energy, the nuclear repulsion, and this term E sub A is eigenenergy of the electronic state at provided interatomic distance. So then all acting on unknown nuclear wave function given eigenstate and nuclear wave function. So the total energy is composed of kinetic and potential. Kinetic is here pure kinetic energy, and potential is contributed by just simple nuclear repulsion and eigenstate of electronic problem. So one can think that this electronic term is added to the nuclear energy. Electronic term is added to the nuclear energy, and we redefine nuclear interaction. So this stuff in the green circle, in the green highlighted thing, is updated nuclear repulsion. Sometimes this term may be not repulsive anymore. We can put like prime or tilde, and this is referred to as potential energy surface. I will be not surprised and not offended if some of you or all of you hate equations, but the concept of potential energy surface is something more general and valuable, often used in practical chemistry, not only computational and theoretical, but also in wet chemistry. The concept of potential energy surface is similar to like potential energy depending on nuclear distances. And main message from the slide that this dependence of energy on nuclei to nuclei distances on bonds has some contribution from rearranging electronic clouds. The little homework, which is less important than presentations and that will be offered with due date on next Monday, will include an invitation to look online and provide just brief definition in graphical form. What is potential energy surface? The definition here is a little bit dry and boring, and one can define it much more colorful by plotting some examples or borrowing some equations. Why one needs potential energy surfaces? So, and why they have, I'm going one slide back, why they do have index E sub B. I understand you may be already tired and irritated, and I'm going a little over time with these slides, but this is another important comment with more general implications. And I'm going to communicate a concept that you may already know, or you may easily absorb because it's quite general and can be communicated without equations. So the potential energy of molecule depends on interatomic distance when the molecule is in the ground state, right? But if we promote the molecule from the ground state with certain equilibrium, and if it oscillates near equilibrium, it will be some potential surface, parabola or multidimensional parabola or something more complicated. But if one excites the molecule from ground state to like first excited, second excited, there is no guarantee that the equilibrium position and shape of potential will stay the same. Yes, V sub Nm, blind, pure, and basic Coulombic repulsion between nuclei will stay the same, but in excited electronic state, shapes of electronic clouds will be different. They will screen Coulomb interaction differently, and therefore potential between nuclei will be different. So potential energy surface will have different, like here we have V sub Nm plus E sub B equals 0, which is ground GS, ground state. If B equals 1, it will be first excited state, and the equilibrium position will be different, and shape and curvature of potential energy surface will be different. If one excites it further, the potential energy surface may transform even further, and instead of attractive, instead of conservative and bringing system close to intact bond, it may become dissociative potential. And this is one of the basic ideas of photochemistry. So if one excites in another state, the bond may break naturally as soon as you excite. Potential energy surface becomes not conservative, not attracting to the equilibrium position, but just goes into infinity. So it's photo decomposition of molecules. We are going to neglect these properties for like mid part of the course, but we will return to it at last, let's say, 3-4 weeks. I have more things. I may have more things, but let me make a little stop and break here and ask other questions or objections about this idea. Janice?
Hi, sorry, I didn't hear part of it because my internet went out.
No, you were already on the connection. I'm asking only about the last slide.
Oh, only about the last slide. Yeah, I don't have any questions about it. I do have some questions about previous slides, but I'll probably get to that later.
Okay. We can organize your questions either returning while everyone is here, or we do the whole program with a practical exercise, and when everyone departs, we can go through slides and I will do one-to-one and answering questions. We'll decide it on.
Yeah, let's do that. Yeah, we'll do the last thing you said there. We'll just talk about it afterwards if you're okay with that.
Kristen, please, if it is problematic to speak, if you are in the lab, you can just type if you have any questions or objections about last slide. Or no? Okay. Thank you for supporting. You? Okay, thank you very much. I'll take your notice of no questions as a vote for accepting last slide as correct. But I think it should attract your attention, and it is the slide was prepared before many years ago, but I think it will be especially applicable to the research problem that you is doing. Okay, so the neglection of non-adiabatic coupling is called BO, Born-Oppenheimer approximation. And in some sense, it can be interpreted as there is no jumps. There is no jumps between different potential energy surfaces. So if we neglect this response of electronic wave function to elongation of bonds, then it, through some derivations, the consequence is that one cannot jump from one potential surface to another one if the even if system is in the high amplitude motion. But if we are at the bottom of the ground state potential energy surface, we do not need it. If one heats system up or photoexcites, then one needs to bring this Born-Oppenheimer, non-Born-Oppenheimer terms back. So, nuclear wave function. How many slides do you have? I need to stop maybe before we go to the end, but I need to switch the gears and maybe talk more than showing slides. Did any of you experienced importance of nuclear properties of nuclei? Or did you hear about nuclear, like nuclear corrections, 0-point energy, tunneling? What do you think? Is it important or negligible? Janice?
I believe it is negligible because most of the particles associated with nuclei are somewhat at the classical limit. They're kind of in that interface between classical and quantum limit, and I believe that they're considered bosons. So I don't think you necessarily have to worry about tunneling or anything like that, particularly.
Thank you much for the support. Kristen, do you echo the point of view of Janice, or you want to add something? I would agree that they're negligible. Okay, thank you, Kristen. You? How, from your point of view and experience, how important is the agree? Okay, so yes, you were correct. Thank you, Janice and Kristen and you for practicing your scientific intuition. In most cases, the wave function of nuclei is not needed. Although rigorously mathematically we got equation for it, we know that it does exist, but we need to be more practical and convert this equation into something more reasonable. I also want to bring up, just a second. Okay, I want to bring up, here is the slide panel with questions. If I look onto the lower left, there is a list of our discussion, and you was asking, do we also learn molecular dynamics? It's a perfect question, mostly relevant to what we are doing, although it may not be seen immediately. So we need to follow the question of you and introduce molecular dynamics. So in some sense, the question is how to get molecular dynamics out of this equation. Right now, this equation no way looks like anything reminding molecular dynamics, but we need to philosophically go there. So there are two components. One component is that we need to get rid of quantum properties of nucleus. It will be our another approximation. So approximation number one was Born-Oppenheimer. Second, that we are going to neglect quantum properties of nucleus. And we need to bring in dynamics. Dynamics means T, right? Time dependence, letter T, symbol T. Right now, the equation does not have T. Where do we get it from? I would like to ask a little help from Kristen. Can you please tell whether this equation, this Schrödinger equation, is time dependent or time independent, and how to convert from one to another? Kristen? Do not just say yes.
Yes.
Okay, good. So, have you seen before conversion between time dependent and time independent Schrödinger equation? Are there something common and different, and just comment briefly on that?
Well, if I remember correctly from your quantum class, essentially the difference between the two is that the time-dependent Schrödinger equation depends on time, whereas the time-independent will depend on energy.
Okay. And is there something common in both of them?
The Hamiltonian.
Super. I'm very happy. Thank you. You did deserve your grade in the quantum course. So we keep the Hamiltonian. We add the dependence on time in the arguments of the wave function. And instead of eigenenergy here, we put time derivative, ddt, over this chi of r comma t. And as a price to this transformation, we put imaginary unit and Planck constant. So if you do this transformation, we keep the same philosophy, same Hamiltonian, same space of independent variables, but now we are in the time-dependent Schrödinger equation. So ddt, unknown wave function which progresses forward in time, the same Hamiltonian as it was before, some constants, and the wave function here. So it is natural conversion between time-dependent and time-independent because they both use the same Hamiltonian, they use the same space of independent variables. Okay. So wave function is distribution in space. And if you have only one nuclear coordinate, which is rare, it's only for diatomic molecules. It means it is distance between nuclei, right? Then the wave function is amplitude of probability distribution that atoms in diatomic molecule are positioned at certain distance from each other. So it will be, if the probability is more at certain distance, it will grow up. If it will be less, it will grow down. And if it moves with time, it will also accumulate some fringes. So there is no much time in this course to get it, but Kristen got it in last fall, and Janice hopefully will get it in the coming fall. So the typical solution for nuclear wave function looks like this fringes around the elongation, the bond distance. So highest probability is when the atoms are positioned at their bond lengths, and there is a probability that they have a little more or a little bigger bond lengths with a certain probability, but if we contract or expand it substantially, then probability quickly decreases. So even if we carefully solve time-dependent Schrödinger equation for nuclear wave function, we will find that it will be fine distribution near interatomic distances. So let me scroll back to my mind. We already did two approximations. We did one, Bornik and Heimer, uniglatic, non-adiabatic. We haven't done, but we are planning to neglect quantum properties of nuclei. And here is our moment of glory in the sense of becoming more efficient. So this distribution that I did draw with purple, the distribution, does have certain width. So if the width of this distribution approaches zero, if it becomes narrower and narrower, then one can replace this yet unknown wave function by very, very sharp function with zero width, which is called Dirac delta and symbolized by this symbol here. And you see that this delta, Dirac delta, and in the brackets we have interatomic position as independent argument minus r in the angular brackets, which means average value of the interatomic distance. So if distance is equal to the average interatomic distance, it will be sharp spike. If it is not, it will be zero. So if we accept this intuitive conversion of nuclear wave function from continuously distributed function to just single delta function, then look at me. there is no reason to speak about function. If you know it for sure that it is delta function, we need only to focus on the expectation value of interatomic distance. So we need to perform conversion of time-dependent Schrödinger equation into equation for this average interatomic distance. And this is typically done. So we go from wave function, which may have some oscillations. It has Gaussian shape with fringes, but we convert it into the center. And this conversion into the center is we do not have time, and we are not going to do it rigorously. But the chapter of quantum mechanics is called is related to Ehrenfest's theorem, and if we carefully perform this transformation of the I think I left it for the next meeting. So if we carefully replace this unknown wave function into delta wave function, r minus expectation value of r, then one can replace Schrödinger equation with second order Newton equation of motion for the average interatomic distance. One divided by mass, and here is the force. The only question is how to compute this force. That I think is too much for today. We need to focus on it next time. So I have a question to you. Do you qualify this equation as a sufficient answer, or maybe as a first step towards your question, if we are going to do molecular dynamics? If you think it is not sufficient, feel free to say. I will address. Okay. Thank you for confirming. So as soon as we do have second derivative of position equals to the force, which is Newton equation, foundation of modern science, it means we can quickly, or someone can do it for us, quickly program trajectories of this angular brackets R, and it is basically called molecular dynamics. So as soon as one has Newton's equation of motion for positions of ions, this is molecular dynamics. So in some sense, we are moving from overall molecular Schrödinger equation to chopped, separated electronic and nuclear degrees of freedom. And then for nuclear degrees of freedom, we get rid of quantum properties, and skipping some steps, we are arriving from time-dependent Schrödinger equation to Newton equation of motion, which is a molecular dynamics. Okay. Whew. So why we are done with theoretical part? I just want to give a little context where we are and why we do need it. Why we do need it. Our goal is to find equilibrium geometry of each molecule. And I can scroll here. So our goal is to find this equilibrium position, the value of this R equilibrium for any given molecule, for any number of degrees of freedom. And if we start geometry somewhere away from equilibrium in the space, in this phase space of positions, we need an algorithm that will drive us from random initial geometry or human geometry that we draw as humans, that give some steps that will bring us to the true equilibrium geometry. And molecular dynamics is not intended to bring us to equilibrium geometry, but it is very similar and very close to the algorithm that changes geometry from non-equilibrium to equilibrium. So we did arrive to Newton's equation of motion and to molecular dynamics as a step towards finding equilibrium geometry. Whew. So done with the theoretical part. We are going to go over practical steps that we did last time. I will probably bring up the questions for presentations on the 1 week and 2 days from now. And I do see that Janice has logged into the sign up sheet, but still there are no choices. So I'm going to go over practical steps, and if we do not have a strict plan, we will just look on this list and figure out things from here. So for Kristen and you, please look onto the questions that you have selected, and maybe the best way, most practical way, if you already open little blank PowerPoint and start preparing presentation, filling it as time goes by. So I will first visit with Janice, and then visit with each of you, looking how happy or unhappy you are. And we need to make sure we are on the same page. And coming Wednesday, I will cover all subjects that we didn't cover yet. Okay. Yeah, thank you, Janice, for making the first selecting the first subject. So, Janice, which computer platform do you use, PC or Mac?
I use PC currently. I'm not very experienced with Mac, so.
No, it doesn't matter. I will adjust to whatever you have.
Yep.
So, did you watch the materials from previous meetings, or how early should I start? Should I start from the beginning, or you already have some idea of what we were doing here in the class?
Oh, I already have like some idea to some extent. I haven't gotten to a couple of the sort of post-lecture, or I haven't gotten to the post-lecture part for lecture 4, but everything should be good besides that.
Okay.
I think really more than anything, what I missed today was just like a couple of slides that I noticed. Yeah.
So, were you able to log into the Photon server?
No.
Okay,
not with my own login, at least. I still have to sign up for a CCAS account, but I can log in as of right now. Do you want me to log in real quick?
Into Photon.
Oh, into Photon. I have no idea how to do that. No.
Okay, I will show it.
Okay, gotcha.
So you are typing do you see my screen?
Yep, I do.
Okay, so it is very much recommended to use MobaXterm.
Yep.
Okay, and you open session and type this, just copy paste this stuff.
Yep. Okay. Yeah, I remember this part actually. Sorry about that.
Okay.
I
Okay.
just
That's okay.
give me a second.
And please check your email for secret word.
Okay, gotcha.
Did you get it?
Just about here. Just give me one moment. Oops.
And for Janice and Kristen, oh sorry, with Janice we are visiting right now. For Kristen and you, you can be a little irritated and upset that we are moving slowly, but we need to all to be on the same page. If the best investment of time is to look to your future presentations, and I believe I did shared presentations from last year's either as PowerPoint slides or as YouTube links. So you may feel free to borrow elements or just inspiration from there. Janice, were you able to log into Photon?
Yes, I am
Okay.
just getting there. Yep.
Okay, so I assume you are familiar with Linux vocabulary, right?
Yep.
So you see right now, after you log in, you are in the home and user directory.
Mm-hmm.
So there is this home doesn't have enough space for our exercises. So we do need, kind of like on CCAS, there is a scratch space.
Yep.
We do have a space available for our exercises in the course. I did copy it into the common chat.
Yep. Will do. Oh.
And please, oh, I already see. Oh, okay, okay. So you were able to log in and create some files. Very good.
Yep. Yep. Yep.
Yeah.
Let's see here.
So, please try. I believe you already have access to Ghost View maybe on other platform, but please check. Please check if you can access Ghost View here.
Okay. Yep. I have done that before. Yep.
Okay.
We did that in the second lecture. I remember that.
Okay. So can you open this software?
Should be able to. Let's triple check. There we go. Yeah, it just opened. Mm-hmm.
Okay. So what do we have and why we need it? The Gaussian and Gauss View software are assumed like golden standard for chemists because especially for experimental chemists, because it is very intuitive and quick to start with. This is not only one and unique. There are some software that does the same function. Mm-hmm. But this software has three goals. So first, create atomic model. Second, prepare input files to be submitted in the queue to compute something.
Yep.
1, 2, and third, analyze and visualize results after they have been computed.
Okay. Yep. So very similar to Avogadro. Yep.
Exactly. And the number 2, preparing input files, is something valuable that we will definitely use. So please make yourself comfortable in navigating this mouse-operated panels. And
Yep.
I have a, please try to click inside the white box and see if you have anything appearing.
Yep. Looks like I'm getting an ammonia molecule in there.
Okay, okay, very, very good. So then probably you are on campus and you have quick connection.
Yep.
Very good, very good. Because some of us who are away from campus have it substantially delayed and or even not visible at all.
Oh,
So
gotcha.
please practice on clicking several times and see if you click on the side hydrogen, it should continue like chain of carbons.
Yep. Yep.
Okay, and probably if since your connection is the quickest, would you please share your screen?
Oh, yes. Give me one moment here. Okay. Gotcha. Alrighty. All right. Everything look good here?
Okay, okay. So let's do a little exercise. Instead of typing things myself, I will just suggest you what to do. So try to array. Yeah, keep this one. And now you have a methane. Let's click once again to have a methane.
Yep.
Just click once.
Yep. Yeah, it's not showing up. I think it's because I might have deleted that. Here, do you mind if I quick restart Gaussio real quick?
As you wish. And since we are on the remote connection, everything is delayed and we shouldn't be surprised of it.
Yeah.
If you would be on campus, it will be instantaneous if you would be in the room nearby the server.
Right. So it looks like I already have 2 sessions. Okay. No,
but just be patient and do not click quick. Just click and wait.
Yep.
Okay. So let's click once to get the ethane. First methane, CH4. Click and wait. It will appear.
Yeah.
Now, click once on the hydrogen, which should create ethane, C2H6. Okay, now, yeah, rotate it slightly. Yes, so everyone recognizes it as a thing. So I'm going to introduce, with your help, 3 basic functions that we need for model building and drawing. In the menu, so there is the menus are duplicated. There is one list of graphical elements in the main panel under the words, and they're duplicated in the little builder that you have on the left from your white screen.
Yep.
So there, yes, there is 2 spheres separated by distance, which is modifying the bond. Can you click on it?
Yep.
Just wait a little. Now, after you selected this option, slowly click on first carbon and then on the second carbon. So what do you see?
So I see a bond semichem, window pop up, and it has bond type, displacement, bond length.
So please try to click on different bond type, just
Okay.
as an exercise. Now it has, just click and see what happens.
Okay.
So it just draws double bond. Keep going.
Okay.
So it draws triple bond. So let me make a comment. What you have done. Those are very basic operations, but the comment is worth to offer right now. Very soon, in 2 weeks from now, we will go to electronic structure, to methods that deal with electronic wave functions. And there, the only input about molecules will be positions of nucleus. The information about chemical bond will be absolutely irrelevant. But now, for next week, the bond type does make sense. In 1 or 2 lectures, we will introduce so-called force field, which means instead of solving a Schrödinger equation and finding electronic contribution to potential energy surface, one uses pre-made databases, pre-made information about potential energy surface for each type of elements, for each type of bonds between them. And depending if we will be using force field, the type of bond will change the style of interaction between them. So this is only temporarily tool, temporarily information, only as long as we use so-called force field. As we neglect force field and go to true ab initio methods, this bond will not be so important. So you did return to a single bond. Now there is atom 1 translate group, atom 2 translate group. Okay, if you click, you will see that one can change it, right?
Yeah.
Maybe fix, atom 1 fix. Click on fixed. And second, keep translate. Now under this, there is a bar that you can pull. Please practice slowly pulling it to the left and right. So this is a tool to modify bond distance. Automatically, it offers some value which sounds reasonable from chemical intuition of the software or agrees with database. But if you want to do something unique, or if you want to model chemical reaction where bonds are broken or formed, you can change your reactants or products or transition states. So maybe elongate it a little bit so it will be not boring, and then click OK.
Okay. I'll just keep it at that.
Can you do it longer, like 2 angstrom?
Sure. Oh, I need to click on something else here. There we go. And I'll click on these 2. All right, and then 2 angstroms.
Okay, and just click OK. Now, we created something that is likely unphysical. There is a way of to improve the geometry, which will relate to optimization, which is not a true optimization. So it is something away from algorithms that we cover in the course. So it's so-called cleaning the structure. So if you navigate to the broomstick symbol and click on it, look what happens.
Yeah.
Please verbalize, what did you observe?
So it shrunk the bond length and might have rotated a couple things around. We'll see.
So to original, this broomstick uses databases for most typical distances and angles. So it is not reliable for any publication on true science. It only simplifies initial geometry, but it's a tool for building molecules. Now, next to modification of distance, there is a modification of angles. Can you please click on it?
Yep.
And after window pops up, you may click on 3 atoms. First carbon, second carbon, and one of the hydrogens.
Okay. Oh. There we go. There we go.
Okay. So please practice pulling the bar to the left and to the right slowly and see what happens.
Okay.
And you can verbalize it because you have very quick connection. It's beneficial for the rest of the classmates. So.
Yeah. So essentially, carbon 1 and hydrogen 3 are having an angle between each other, and we're centralizing that angle on carbon 2. And so when you shrink that angle, they become closer together, and when you enlarge that angle, they become farther apart. For instance, when you pull it to 180, it'll be completely straight. You know,
okay.
When you pull it to 0, it'll be together.
Excellent, excellent. Please do like 180.
Okay.
Some extreme case, and click OK. And now let's practice broomstick once again to check whether it will fix it back. Okay, it does. Now, next to the angle modification, there is one more symbol that shows 3, yes. So can you explain what the symbol means based on your chemical intuition?
So my intuition is that this is based off of torsion angles.
Excellent, excellent. Question to Kristen and you. Would you please offer any different word for this torsion angle? Like in chemistry, which words are used for the torsion? No answer. Okay. This was a new word that I learned long after finishing all my degrees, because they were not in chemistry but in physics. So the word is dihedral. I think those who chemistry majors may recognize it. So
yes. Yeah.
Right. So Janice, please make us a favor and click on 2 carbons and 2 hydrogens. Select this dihedral modification, and let's start over. Okay, 1, 2, yeah. Maybe start over and go on to hydrogen, carbon.
Hydrogen first.
Hydrogen.
Yeah.
And now practice pulling slowly this tab to the left and to the right. So it looks like screw and not rotating in respect to each other, right?
Yeah.
So please try to put it some untypical value and click OK, because we are going to practice broomstick again.
Okay. Broomstick.
Practice, yes. Okay. So I do have a couple of questions that you may explore yourself and report if there will be time in your presentations, or so how to remove an atom, or you can try doing it right away, or there is a little red cross if you select it in the menu. So try to remove an atom. Okay, you removed this group. Okay, and question number 2 is how to. So it will be more complicated. And the question I'm going to ask could be of interest to all of us, and maybe especially for Kristen. So suppose we need to model a polymer when the same chemical group is repeating periodically again and again. So basically, try to explore this Gauss view software and find an option to copy a fragment and then paste it again and again, to have a repeated unit.
Okay. I'm guessing that's with the marquee box here. So you can just marquee a group, and then you can Control-C, Control-V.
Please try if it works.
Yep. Oh. All right. What's my clipboard right now? All right, that's my clipboard. Let's see. So it might have worked. I can't really see though. Let's see here. Yeah. I don't think it worked properly. Nope.
But please try to find answer on this question later. There is a very extended manual for Gauss view on the Gaussian website. If in any browser one types Gauss view manual, one can read a lot about it, more than we need. And I gave the link in the syllabus, but you can just find in Google, like type Gauss view manual.
Okay.
So now, please make this molecule back to ethane or something reasonable. Right now it doesn't mean what.
Okay.
Just put a hydrogen or another, just do something.
Yep. Oh, I see. Okay. I see what that did now. All right. And then I will go back to my other one here. So we'll click on this, and then we'll bring this over. So just click this. See how it goes. There we go.
Very good, very good. Please do it. No, keep it as is. Now, please bring to the front the main panel with menus.
Understood.
Yes, this one. So please navigate to the 4th menu, which tells calculate. And select the first one, Gaussian calculation setup. So what do you see?
So it looks like a job menu. So I'm guessing that it's turning this molecule into a file of coordinates, or whatever sort of file you want.
Okay. So there are several tabs, and first tab is job type. Can you click on this energy and tell what else is available?
So it looks like you have optimization for geometry, frequency, optimization plus frequency, IRC, scan, stability, and I'm guessing an NMR simulation of some sort that creates an NMR spectra.
Okay, so in the future, we may explore scan, but now if you consider yourself as chemist, scan is a way to literally extract potential energy surface from by calculations. But now we need to optimization. Can you click on it?
Yep.
And now there is a second tab that tells method.
Yep.
Can you click on it?
Yep.
So the second sub tab tells hardware fork. Please click and tell what you see.
So this looks like different approximation methods or methods of calculating optimization geometry.
Okay, so the methods are arranged from simple to more complicated, or from cheap to expensive. So the least precise and the cheapest is mechanics, otherwise called force field. Please click on it.
Mm-hmm.
And UFF is universal force field. So there are other options, but now for basic jobs, we do not need more. Please click on the submit at the left bottom.
Okay.
And tell what you see after.
You must save a Gaussian input file before submitting.
Yes, let's save.
Okay.
And there will be option to name it. So click on Genesis so it will be not mixed with other. Yes, and give some name like ethane force ethane underscore FF OPT for optimization. Something unique that you can recognize.
Okay. Okay.
Now click save and tell what you see after.
Okay, submit the file, do Gaussian, okay.
So do not do anything. Let me, oh, you already submitted?
Yep.
So do not do things. I want to give a comment before.
Oh, okay,
So,
understood.
So when it was asking you to submit or not submit file to Gaussian, currently on this server, Gauss View is automatically connected with Gaussian, which is very comfortable environment, but not every server provides this connection. Also, some of the classmates have problems running Gauss View. I want to bring up that preparing model and preparing task for computation are different from doing actual computation. So at the instant of time when you were about to click submit to Gaussian, there is a like borderline before preparing model and running model.
Yep.
Why I'm so boring and careful about this? Right now, when we do this ridiculously small molecule, and when we do the cheapest method, you see that results are offered even before you can breathe. But this is limiting case. As soon as we use more reliable and more expensive methods, and as soon we are going to larger models, the time from submission to obtaining results will increase by orders of magnitude. And simple servers like this Photon, it's not a very powerful computer, will be not physically able to do the computation. I'm sorry for being very long in this disclaimer, but it is an important part of the philosophy of practical jobs. Just a second.
Take your time. You're good.
Yeah. See.
If you would like, I can demonstrate some of this in Avogadro as well, if people need an Avogadro sort of, you know.
Not right now, but thank you for offering.
Okay, gotcha.
So it's many words, but practical aspects right now look simple. So please click on the second option, the file that ends with .log.
Okay.
And say OK. So this is, and if you click away from the molecule and keep clicked, and you can rotate and look on the molecule from different aspects.
Okay.
Can you? Yes. So what is the difference? What is the difference between molecule that you did draw by your hand and the molecule that you see right now?
Likely more accurate scaling and bond lengths, angles, etc.
Okay, how to report it if you want to write paper about this ethane molecule?
I'm pretty sure you can go to the specific functions for dihedral angle, regular angle, and distance.
Exactly. And then when you click and do not modify, it just shows the value of bond lengths and angles and dihedrals for any groups of atoms, right?
Yeah.
And it's probably not of big scientific value today, but if we would live like 30 years ago, we could publish a paper, like optimize geometry and report how angles did change. Okay. So also, if you bring up the main panel and click onto results, there should be a summary. So about 8 lines from the top, there is a total energy.
Mm-hmm. Yeah.
Do you see it?
Yeah. Yeah.
So this number can be also like copy pasted or just typed into a table. If you consider several conformations of the same molecule, you may associate conformation with the value of total energy. And the basic idea is that the conformation that gives lesser energy is more probable. Does it make sense?
Yep.
Okay, very good, very good. Now, you do not need to close this Gauss-Lie window, but please bring up your MOBA extern.
Yep. Okay.
And do ls. cd Genis, go to your directory.
Oh, sorry. Oops. I forgot the capitalization.
It's case sensitive.
Yep.
ls. Maybe better ls space minus lt. So last created is showed at the top of the line. So we do see 3 new files from today: ethaneffopt.com, ethaneff_opt.chk, and the same .log, right?
Yep.
So the one that ends with .com is input. The one that ends with .log is output. Can you please do more, M-O-R-E, space, ethaneff_opt.com.
Oh, right. Gotcha.
And just please explain what you see and how you interpret it.
So,
starting from the first line.
yep. So from the first line here, this shows the title of the check log, which is basically just sort of intermediate log of what sort of calculations that the program did. The second line here, that looks to be just what kind of computation that it is. Nothing really special there.
Wait. What does mean OPT and what does mean UFF?
So optimization for OPT and UFF is the type of, or the calculation type used, which is universal force field.
So let me make a comment.
Yep.
The mouse-operated graphical user interfaces, as other members of the class noticed, could be unreliable if the connection is slow. And it's only a question of luxury. In fact, one may borrow geometry, which we will discuss in a few minutes in the Cartesian projections, and create the input file for Gaussian just by typing in keywords. So if you know that you want to optimize by UFF, you do not need to open Gauss U. You can just add this line and manually type it, right?
Yeah.
Good. Hello, Jayanta. Thank you for connecting. Okay, your mic probably is off. Message for Jayanta. There is I was trying to record all meetings, and I'll share them with you so that you can look a few previous meetings. And today we are going to finish soon, but you can just get a general impression and see what we are doing. And then we will exchange more by emails. Back to Janice. Skip. There is an empty line, then title card required, then empty line. And what is 0 and 1?
0 and 1. Oh, goodness. Trying to remember here.
And
I believe that is charge and spin. I remember seeing that specifically in the menuing. There was 0 charge and then a spin of a singlet. So
excellent. You can get credit for this course right away. You already know things. Excellent. So if the 1 stays for singlet, what will be the code for triplet?
Triplet.
Everyone is welcome to type answer.
Yep. My answer, I believe, is 3.
Okay. Anyone wants to object? Answer by Janice. No one. Okay. Yeah, because it was correct. Which number should? Yes, 2n plus 1. U is correct. Or sometimes people use the s, 2s plus 1. S for spin 1/2. So what would be the spin index for doublet?
Doublet spin index for doublet. Actually, would that one be 3?
No.
I'm actually kind of curious. Oh, no, 2 then. Okay.
So the equation that you typed in the chat line, which is 2n plus 1, gives a prompt. Okay. So if the n, and typically one uses the letter s, the spin. So doublet is spin 1/2, right? And this 2s plus 1 is multiplicity. So if 2 times 1/2 plus 1.
Oh, we're talking about multiplicity. Okay, gotcha.
So the index, second index after charge is spin multiplicity.
Okay, yep.
The equation suggested by you is absolutely correct. So if spin is 0, you plug in 2 times 0 plus 1 equals 1. Multiplicity 1, singlet. If spin is 1/2, you plug in 2 times 1/2 plus 1 equals 2, right?
Yeah.
If spin is equal 1, 1/2 plus 1/2, two unpaired spins. then 2 times 1 plus 1 will be 3. Multiplicity 3.
Gotcha.
So charge and multiplicity. Now, what are the next after 0 and 1? What are those numbers?
So these numbers and letters signify what bonds and what their coordinate positions are, or what bonds there are, what atoms there are, and what their positions are in Cartesian space.
Okay. And the most standard is just give positions, Cartesian coordinates of each atoms. And it is more reasonable for ab initio calculations. But for force field, sometimes it uses this connectivity by giving explicitly the direction of each bond. So these three Cartesian things are vectors connecting atoms. So please type tail, like tail of mouse, tail space, and then the name of your output files, ethane underscore ff underscore opt.log.
.log or .check?
.log. Do not look inside .check. It is you can see that it is big file and it is.
It would take a while. Yeah.
Yeah. So what do you see as the very last line?
The very last line, normal termination of Gaussian 09 at Monday, June 8th, and then the time, date. Yeah.
Okay. So in a very narrow sense, the job of computational chemist is to convert, or job of computational software is to convert .com into .log file, right?
Yeah.
Now, how do you know, or how do we know if the job has been completed? The .log file is being filled. So as soon as Gaussian code is running, either on a standalone server or on a cluster, the .log file is in incremental way getting more and more lines as calculation goes on. As sometimes we may want to double check if the job has completed. On the other hand, sometimes job stops with error and gives some nonsense. So this human language writing normal termination as the last line of the output file, of the .log file, is a signature that the assignment that you gave to Gaussian software has been completed successfully. Make sense?
Yep.
Now let's try to do very brave exercise. Let's type grep, G-R-E-P, space, lowercase energy.
I'm sorry?
Energy, space, and then type the word energy. Space, and type the name of your output files, ethane underscore ff underscore opt.log.
Okay, gotcha.
And hit enter.
Okay. Oh, I see. Okay. I forgot the E there. I'll fix that here real quick. There we go.
Okay, let's practice a little bit more. And do you have arrow up on your keyboard?
Yep.
Click once, then click arrow left, and replace lowercase energy with letter E to uppercase E.
Lowercase e to uppercase e. So then we'll just go to capital E
Just-
energy.
Yeah.
Okay.
Hit enter. So, what do you see?
So step on SND rises, scale max 4. Noticing a couple of words there. So it looks like it tagged this line specifically. So it shows the energy and some other value that I'm not 100% sure about.
Okay.
And
Good.
Yep.
Do you have pen and paper in front of you?
yes, I do.
Can you please write down this value? You do not need many sig figs, like 2.2 times 10 minus 4, right?
Yep.
And now let's go back to Gauss view.
Alrighty, understood.
And check the total energy that you have highlighted with black.
Yep.
How similar or different are those?
They seem pretty similar. This one is a little bit different, but barely by anything. Instead of a 1 there, it ends up in a 0 and then continues.
Okay, so it is 2.2 to the 10 minus 4, right?
Yep.
Okay, so what is the comment to this observation? There are two ways to analyze results of calculations. One, more luxury and human friendly, is to click results and see the information being offered to you in the comfortable way, right?
Yep.
Second way is less comfortable but much more reliable. If you go back to the mobile extern.
Yep, give me 1 second here.
Like alt tab simultaneously, if you know how to switch between windows.
Yep, I know. Sorry about that. It's just I was writing something down.
That's okay, that's okay. So one can get the same information just by analyzing output file. And the total energy is a main observable for all, not most, all quantum chemistry calculations. There are some additional observables, but the total energy is the main thing that is computed always. And one can extract this main observable without using this graphical interface. Just looking onto the file and scrolling until you see the keyword upper energy started with uppercase. Make sense?
Yep.
Good. Let's. I think we are running out of time for today. Let me look on what we have on our list, and then answer questions. So we practiced Linux environment index connection, although we didn't discuss it today, but we discussed it before. Uploading, downloading of files. We discussed it with Kristen, Yu, and Mahima, and Yu is presenting it. But Janice, do you know how to up and download files?
Yep.
Oh, I need to share screen because I'm looking on the list. Sorry.
Okay, I'll share mine.
It sounds a little strange. Okay. So we did Linux environment, files load up and down, account on CCast. Janice, since you are helping to system administrator and serving some roles, I think it would be very appropriate if you teach everyone how to do it.
Yep, I will do just that. I was just about to sign up for it, and also Linux environment.
Super, super. If you can comment on job submission, would be also cool.
Understood.
So run goes you. Mahima did sign up, but today we went over it. Build atomic models, we went together with Genius. Modify distance angles, dihedral angles, we also did it. Clean optimize geometry, we did it. I think you may add this one to your repository. Convert formats. Genius didn't practice it, but we did it last time with you and Christian and Mahima. JMO is one of the replacements of the Ghost U. It has a little less functionality, but it quite useful. We didn't cover X-ray diffraction, and I think I need to make some demonstrations when we meet on Wednesday. Avogadro, we covered it. And Hypercam, I don't think we have time for it, but it is just recommended. This is commercial software, but test version is available, and obsolete versions, I would better say it this way. Never download pirate software for paying nothing, even if you know where to get it. And we do not include it, although this is quite good software for building models. So basically, we almost ready to present, although we will be doing it in a week and 2 days. Let me check other questions. Kristen? Oh, I see a question from you. What does the tail command means? I'm answering to you. The command more does show the whole file. Command head, like head of a person or head of animal, shows the top portion of the file. The command tail shows the last portion of the file. So the file.log that Janice was demonstrating to us today is not super long, but as an human, as an impatient human, I didn't want to scroll through the whole .log file. I prefer to look only on the last few lines, and then I type tail space and the name of the file. It shows only the end. Is it enough? Good. And also there is, if you have seen what Janice was doing, there was a grep command, which means parse the line with a certain word. Grep, some expression, and then file. And then it will pick up the line that has this regular expression out of big file. Kristen, do you have any questions or suggestions? Excellent, excellent. Jayanta, I will share links to recordings, and after watching them, you may get questions, and there will be review of all practical materials by class members. You may, ideally, you may select some subjects before next, not coming, but second coming Wednesday, or if it is too soon, you can just watch what others are doing and get credit from other activities. But it's train didn't departed too far, you can pick up all things and by watching the recordings. Janice, do you have questions?
Yeah, we were gonna talk after class a little bit.
Okay,
Yep.
good. Then I suggest that we disconnect for today. I will stay online and answer a couple of questions for Janice, and we meet next time 5 p.m. Wednesday on the same internet address. Thank you much for your dedication for the course. If you have, oh, my pleasure. If you have some suggestions, if you want me to adjust the program, or you have some, you want me to focus on something or skip something, feel free to send email.
I have a question. So in the Avogadro, there is no like binding or other build lock, right? Because there's only elements.
Right. But in JMOL, there is an option to measure the angle and dihedral. The angle and dihedral are most important for measuring rather than for modifying. For most of the models, changing distances is sufficient. So I never suffered from lack of these features in the Avogadro.
Okay, thank you.
Yeah, my pleasure. Okay, so everyone is welcome to disconnect, and I'm ready to answer questions by Janice.
Okay, understood.
Should I bring up the last slides or?
Yeah, so if you could just bring up the last presentation we did. I just missed a couple slides between like 41 and like 35-ish probably. So somewhere in between there. I missed this part.
So where is it the right place, or like should I go up or down?
Go up a bit. I just want to triple check here. I think the last one was the last white page there.
Are you okay with this slide? With,
Yeah,
or,
I've seen that one. Yep.
Okay. Are you okay with this second derivatives?
Yep.
Okay.
Though I do have a question on the mix one, particularly. Since these are matrices that have indexes, can you actually commute those operations to where the reverse of the operation is actually the same as the reverse of the reverse? So essentially what I'm trying to say is like, in the actual equation, there are 4 terms. So there's that first term, which is like the pure ionic term. Then you have your second term, which is like one part of mix one. It's like part of that 2 times. So you have your like del of the phi operator and del of your like chi operator, or not operator, but del of phi and del of a chi, and then the next one is del of chi and del of phi. So I'm curious if those are actually commutative or not.
If there was derivative over different variables, if it would be like R1 and R2,
yep,
one would not be able to commute.
Okay.
But since it is the same variable here, it is okay.
Okay, so it commutes regardless of what it's acting on. So regardless of what that del operator is acting on, it still commutes.
Let's go back to where it is expressed explicitly.
Yep.
I have it maybe in more full version. Yep.
Yep.
So this is pure. This is second order non-adiabatic, and those are two terms you are asking about.
Yep. So I was just entirely curious because I know matrix.
Okay. So no, your question is very much legitimate, but here is a little compensation of errors. One cannot swap the order of functions, and here was chi and then phi, and it should be the same order here. So to be correct, one needs to write it phi sub a here.
Yep.
Chi phi, and also put chi phi this way.
Totally understand that. Yep.
Yeah, thank you for being picky. It's very appropriate here. Thank you for following.
Okay, yeah, no problem. I was just curious, particularly because since these are like matrix forms, with indices and everything like that, I wasn't 100% if they commuted like that or not, because I don't know, I just saw that and I was like kind of a little bit confused as to if those actually properly commuted and everything like that. I know they go away in like the final product because we're not really worried about them, but I still was kind of curious just to see.
They will come back when we consider advanced topics at the very end of the course.
Yep.
And actual research in the area of computational chemistry relates to them, but for basic applied problems, indeed we neglect them. Yes.
Okay. Can we go down to slide 31 real quick here?
Yes.
Alrighty, that was one that we did. Okay, go down to the next slide. I remember some parts of this non-diabatic coupling part, but I didn't see this slide. Okay. Non-diabatic.
All of them are called non-diabatic.
Okay.
And compared to previous slides that we just discussed, there is this term that means, so we add each term by this factors, summations, and this phi sub a, or phi sub b. Phi sub b with this angular bracket should be interpreted as integration.
Yep, integration over that with the real part and the imaginary conjugate. Yep.
Yes.
Yeah. Yes. Dirac notation. And then the middle part's your operator, and then the right part is your the other thing that's your cat. Yeah. Yep, that makes sense.
Any other aspects?
Yeah, just continue to slide 41. I just want to make sure I get this all sort of remembered at least, because I think I miss all of those slides because of my internet. So I'll go up from there.
Should we discuss this slide or go up or down compared to it?
So go down from the last slide we were at, and we'll just cycle through it. I just want to see the rest of the slides that I missed. Yeah.
So.
Yeah.
Are you okay with this one?
Yeah, looks good.
Okay, it's this one.
Yeah.
No, here the cross term, and this derivative over position with this part and this part combined together, we will just give momentum operator.
Yep. That makes sense to me. Yep.
And the meaning of this term, and then we plus second order correction. So this response of wave function to elongation of coordinate will be non-zero only if nuclear momentum is not zero. So only if the molecule is moving, all these corrections make sense. If the molecule is not moving, if momentum is zero, temperature is zero, then one definitely neglects everything precisely.
Yep. Makes sense. Yep. 37. Okay. Matrix elements in respect to electronic part. Okay. So we have our. Yep. That all looks good.
So phi b convoluted with phi a is either 0 or 1 delta function, right?
Yep.
A, b. And when summation meets delta, they mutually erase each other.
Yep. That makes sense. For like even and odd functions, yeah. Yep. Dirac delta, yeah. Or not Dirac delta, Kronecker delta. There you go. Yeah.
Yes.
Yep. Okay. Yep. That all looks good.
I think the same, just without highlight. Then it's basically done.
Yep. Okay.
This is the same as the next one. I just tried to redraw it in a slightly different way.
Yep. I gotcha. Yeah. That looks good. Okay.
Okay. Yeah.
Yep. I don't think I have any further questions from there. I'll do some more supplemental reading, and then yeah.
Okay. Yeah. Let me know if you want. I can share like book chapters in the PDF form if you want to read deeper. It's not necessary for being absolutely successful in the course, but if you have curiosity, I'll be happy to share more materials.
Super. Awesome. Thank you so much. Appreciate it.
Okay. Anything else?
Trying to think here. Nothing that I can think of at the moment. I'll email you if something comes up.
Okay. Then thank you for your interest and attention to little details. I'm very pleased to see it. And let me suggest to disconnect for today.
Okay. Actually, right before then, I almost forgot about this. Did you get my email with my homework PDF attached?
Yes, I've got the email, but I wasn't opening it yet.
Okay, gotcha.
And then in response, I want to check. Okay, yes, you did explicitly signed up for this stuff. Excellent. Yep. Thank you.
No problem. Thank you. Email me if there's any questions on the homework or anything like that, any issues.
Okay, will do.
Alrighty. Thank you so much.
Yep, thank you. Have a good evening.
You too. Bye.
Bye-bye now.